السلام عليكم يا جماعة. نكمل الآن. بدنا نشوف الفلو ديفايسز اللي احنا بنحكي لهم بايبس، وتحديدا هنا بنحكي عن بايب بينز وكيف how to apply the momentum equation to these cases. طيب ناخذ مثال اللي هو بالعربي بحكوا له كوع مفتوح، وطبعا بتعرفوا الكوع اللي هو بيكون بين أنبوبتين على أساس يغير الدايركشن 90 degrees مثلا. This is a 90 degree bend، بينما في حالتنا في عنا bend اللي هو it makes a 30 degree مع الهورايزن. اوكي، بقول لك diameter is 1 meter. The flow rate is 2 cubic meter per second. بعدين it has this angle of turning the fluid اللي هي from the horizon. The volume of oil in the bend، يعني هذا البند because we have a large diameter, it also has a large volume itself اللي هو عبارة عن 1.2 cubic meter. The empty weight of the bend is 4 كيلو نيوتن، يعني كمان هذا لحاله وزنه اللي هو 4 كيلو نيوتن. طيب assume that the pressure along the center line of the bend is constant، يعني إنه the pressure along the center line does not vary and it remains 75 kilopascal gauge. المطلوب find the net force required to hold the bend in place. Once again we have a bend that lies in a horizontal plane. in a horizontal plane، يعني لو بدي ارسمها بدي اقول مثلا في عندي plane بهالشكل هذا الplane represented by x and y direction، وفي عندي elevation اللي هو ايش؟ z direction. Now this bend comes with a pipe like this, and then it turns the flow of the fluid by 30 degrees, but it remains in this plane. So we're talking about this bend. ماشي. Now realize in the z direction, again recognize in the z direction there is no flow. The flow only occurs in the xy plane. So the xy plane احنا بنسميه بالعربي افق، بينما الزد اللي هو elevation يعني بالارتفاع عن سطح الارض. Okay. Again recognize in this problem that the flow occurs فقط only in the xy plane, and also we realize that there is no flow occurs in the z direction. Okay, الآن المطلوب find the net force required to hold the bend in place. ماشي. طيب. So we apply the momentum equation اللي احنا نتذكرها اللي هي عبارة عن summation of forces equal to time rate of change of momentum inside the control volume plus under uniform conditions we have out, which is m dot v minus, of course this is a vector, at the inlet m dot v. Okay, let's apply it in the x direction. So we have in the x direction the summation of forces. Okay, before we do that we need to follow the steps. As he done in the diagram, he's taken the bend by itself and he drew the control volume as you see. Okay, remember when we cut through the pipe here we have fluid pressure. Fluid pressure times area, that's pressure force. Similarly also we have pressure here. Remember that pressure always act on the control volume. So once again when we cut through the fluid we have a pressure times area, we have a pressure force اللي هي acting in this direction. Okay, in addition to these pressure forces we have the force that we are trying to find, which is exerted which is necessary to hold the bend in the x direction stationary. Okay, also we have another force in the y direction, and of course we have another force in the z direction, another component. Okay, so once again, to illustrate, we have the bend, which makes an angle of 30 degrees بهالشكل هذا. Okay, so when we drew the control volume around this bend, the fluid here, which has a pressure free area, that's P1A1, which is a pressure force, whereas the fluid here, always normal, acting on the control volume, we have P2A2. But remember, according to the problem, that P does not vary, it remains constant along this line. So P2 and P1 are equal, but its direction has changed, which is now 30 degrees from the horizon. Okay, and then in addition, we identify Rx and Ry, which are necessary to hold this bend in the X and Y direction, in addition to the Z, which we'll talk about later in a few minutes. So, the summation of forces in the X direction, we have P1A1 minus, notice, because this is acting in the negative direction, we need only this component, which is P2A2 cosine 13, plus Rx, which is we need to find. Always will assume steady. This is obviously a steady flow process, plus momentum leaving, which we recognize from the mass balance, that the massive flow rate in يساوي the massive flow rate out, and we have one stream, so it will become m dot. Now V2 is in this direction, so we need to take its component along the x direction. So we have V2 cosine 13, that's in the positive direction, whereas minus the velocity at the inlet, which is V1. Okay. We also recognize how to find the velocities. Because the areas are equal, it's incompressible, then we understand that V1A1 تساوي V2A2. Because areas are the same, then V1 تساوي V2. Okay, how we find either V1 or V2? Simply by recognizing that the discharge is equal to VA, either at the inlet or at the exit. So in this case, we find V1 اللي هي عبارة عن the discharge was given to us as 2 cubic meter per second divided by the area اللي هي for pipe of 1 meter in diameter. So we find V1, which is also equal to V2. Alright, P1 is given to us as اللي هي 75 kilopascal gauge. Okay, now when we multiply 75, so let's substitute that as kilopascal times area, which is in it will be approximately equal to okay, let's just put area in meter squared minus, once again, 75 which is kilonewton over meter squared. This is what I meant to say. Okay, multiplied by the area, which is in meter squared, plus Rx. Now m dot is simply اللي هي rho Q. We're given rho for water, we usually use 1000 kilogram per cubic meter, multiplied by the discharge, which is 2 cubic meter per second. So we end up with 2000 kilogram per second. Now again we follow this equation, it's equal to 0 plus 2000 now times the velocity, we end up with cosine of 30 minus 1. Then again we have to remember because we're using here kilonewton, is to divide by 1,000 to make the units consistent. We need to divide by 1,000 to convert this newton to kilonewton, because here we get kilonewton in this manner. Okay, this is its application in the x direction. Similarly, we can apply it in the y direction. In the y direction, okay, application of the momentum equation in the y direction. Again, what are the forces acting on the control volume in the y direction? We recognize we have at the inlet we have Ry. Notice that the pressure force does not contribute anything to the y direction, so we have Ry. We assume it to be in the positive direction. Also at the exit we have this component, which is in the y direction, which is time 30. So we have plus P2 A2 sine 30. There is no more forces acting in the y direction, equal steady plus. Now, same thing as we said before, at the exit the velocity is coming this way. So when we decompose it, we have in the x direction and we have in the y direction. Notice how we draw the components. We have in the y direction plus in the x direction equal the velocity. So obviously here we have a negative because we have assumed x in this direction and y in that direction. It's opposing the positive y direction. So this is negative. So we have m dot multiplied by minus v2 sine 30 minus from the momentum equation at the inlet. Notice that there is no velocity component for the velocity, so we have simply 0. Again, by substituting the right number, we have Ry plus 75 kilonewton over cubic meter, as we did before. Area in the meter squared times sine 30 equal to 0 plus, as we computed the massive flow rate, which was 2000 kilogram per second. And then we have minus the value for V2 sine 30, and once again we need to divide by 1,000 to make conversion from newton to kilo in newton. So this is in the y direction. Okay, we're left with the z direction. Again, if we went back to our original drawing, which is this one, in the z direction, we apply the equation, but remember we have no flow, we have no mass flow rate in this direction, so the momentum on the equation on the right hand side will be all zeros because there is no flow rate or no discharge in the z direction, or no tadaffuq. Only we have force balance. So what we have, then we have the normal, which we will call RZ, تساوي the weight, which is downward. So basically this is in the z direction. The momentum equation will come identically summation of forces. We have normal up, or RZ if you will. Okay, let's call it RZ, minus the weight downward, يساوي steady, and also there is no flow rate or no discharge in the z direction. So basically we end up with the RZ reaction in the z direction equal the weight. The weight, remember, is given to us as the weight of the elbow, which is 4 kilonewton, plus the fluid, the weight of the fluid, which we have gamma volume, whereas gamma for the water is 9.81 kilonewton over cubic meter, and the volume is given to us as 1.2 cubic meter. So we end up with kilonewton, and this is the RZ. Here is the solution. You can follow it and make sure that the procedure we followed is exactly what is written on the slides. Here is another example, but this time we have 180 degrees reducing bend, meaning that the flow was in this direction and it turned an angle of 180 degrees. In addition, we have an area the diameter was 30 centimeter, and then at the exit the diameter became 15 centimeter. So that's why he calls it a reducing bend, as you see in this figure. Okay, again we have water, which is flowing at, or the flow rate is a cubic meter, as if 1/4 of a cubic meter per second, 0.25 cubic meter per second, and the pressure at the center of the inlet is given to us as 100 kilopascal gauge at this point. Okay, and bend volume, as before, is given to us as 1/10 of a cubic meter to compute, as before, the weight of the fluid. And we're going to assume that the Bernoulli holds along the center line. In reality, that's not true, because the flow tends to be turbulent, which means that the Bernoulli no longer is valid. But again, this is a reasonable assumption to demonstrate a few aspects for this problem. The metal weighs 500 Newton, density for the water as before. We are asked again to find the force necessary to hold this bend in place. One final note about this bend, that this bend is placed on a vertical plane، يعني زي ما تقول على جدار، على جدار, which we have a flow in the x direction and in the z direction. Notice in the y direction, which is perpendicular to the wall, there's no discharge, and of course there's no force because it's in the perpendicular to the wall. ماشي؟ يعني لو بدي أرسمها بدي أقول this is our wall. This is the floor, and then we have the bend بهذا الشكل. So it becomes large and then becomes a small. So only in this direction, x in this direction, and then we have y لربما inward to make a right hand rule, بهالشكل هذا. So we have x, y, and z is along the wall as he's drawn it here. So again, how to solve this problem? We begin with the control volume. As you see, this is the control volume drawn around the entire bend. 2, we identify the coordinate system that we need, which is x and z. 3, we observe once again, because if the fluid here has a pressure, it will have a pressure force PA acting on the control volume. Notice at the exit also the fluid outside the control volume has a pressure, and it acts on the control volume. Okay, observe this very carefully. So we have P2A2 in this manner. Okay, in addition to the pressure forces, we have the reaction that we need, which is in the Rx, in the x direction, and the z direction. So a point to remember, always when we cut through fluid in pipes, we have always a pressure force. The pressure force always normal and acting on the control volume. Okay, this is a very important to remember for the solution. So we will do the same, we will follow the same procedure as we did before in solving this problem by the application of the Bernoulli as of the momentum equation, which says the summation of forces acting with the control volume, again time rate of change of momentum inside the control volume, plus under uniform conditions we have m dot v minus m dot v at the inlet. Okay, now in here we are given the pressure at the inlet, and he's telling us that the Bernoulli equation holds. It has a flow rate of that much, so we can find V1. V1, it will be basically عبارة عن discharge over area. We're given the discharge to be 2.5 cubic meter per second على area, where the inlet diameter is given us as 30 centimeters, so it will be pi على 4.3 تربيع meter square. So we'll have meter cube and meter تربيع, so it will become meter per second as expected. For V2, similarly, it will be 0.25 cubic meter per second over, now the diameter is 10 centimeter بهالشكل هذا. So we find V2 and we find V1. Okay, we're given the pressure at the inlet to be 100 kilopascal. What is the pressure at the exit? We apply Bernoulli equation, which is P1 gamma Z1 plus rho V1 squared over 2 يساوي P2 plus gamma Z2 plus rho V2 squared over 2. We need to find P2, so P2 equal to P1 is given to us plus gamma Z2 Z1 ناقص Z2 plus rho over 2 V1 squared minus V2 squared. Okay, this will give us V2. Now we need to obviously draw a reference for the Z direction, but this is easy. We can, because he's talking about the center, we can take simply the center point for the exit pipe to be Z equal to 0, so Z2 equal to 0. In this case, if we want to compute Z1, it will be, I apologize, obviously this is not 10 centimeter, it's 15 centimeter. It's 15 centimeter. So to compute Z1, which is this point at the center, we'll say it's half of the 30, which is 15 centimeter, plus the spacing, which is 10 centimeter, plus the 7.5, which is half of the distance here, and that will give us 32.5 centimeter. So this will be the value for Z1, whereas we have chosen Z2 to be 0. Okay, again, water is 1,000 kilogram, as we have seen before. When we substitute for P2 the value, which is 100 kilopascal gauge, we need to remember to divide here by 1,000 to make the units consistent. So in this case we have found P2 as this is P1, and P1 is given, so we have found P2. Now we apply the momentum equation. Let's apply it in the x direction. So forces in the x direction, what are they? We have the pressure force here. Notice it's P1 A1. A1 is being اللي هي correspond to the diameter of 30 centimeter. Also plus, notice, because they are acting in the positive direction, always normal acting on the control volume. And also we have Rx, which we have assumed to be acting in the x direction. Okay, all of this steady as before. Now we have m dot, which is basically the flow rate multiplied by the density multiplied by V2. Observe now V2, it's leaving in the negative x direction, so it will be minus V2 minus from the relation here and V1, V1 which is positive, but this minus, it comes from the momentum equation. again m dot اللي هي عبارة عن rho q density times discharge, which will be 1000 times 0.25, so it will become 250 kilogram per second. Again, we need to remember, if we substitute for the pressure kilo Pascal, we need to divide this by 1000 to make the units consistent. Okay, in the z direction, realize in the z direction we have no flow. We have no flow in this direction, so only force balance. So we have rz equal to 0. rz in the up direction, weight in the negative direction يساوي 0 زائد 0 ناقص 0. rz then it's equal to the metal weight, which is 5 kilonewton, plus the weight of the fluid. So again, it's 0.5 kilonewton plus gamma for water is 9.81 multiplied by the volume. Its volume was given to us as a tenth of a cubic meter. Again, recognize the gamma units are in this manner. Okay, and this will be rz. Again, in the y direction, there is no component in the y direction. There is no component in the y direction because there is no force exerted in this direction except maybe a clamp to hold it in this manner. Okay. يا جماعة, when I was doing this problem, I recognized that I unintentionally call the fluid here water, which is not the case. It's crude oil, and we're given the specific gravity being 0.94. So if we go back to the equation that we were solving before, simply we have to multiply the gamma by gamma. طبعا crude oil is equal to specific gravity for the crude oil gamma water, so we end up with multiplying here by the specific gravity. Okay, unintentional mistake. Okay, we'll continue. This is no problem, you can handle it. Let's look at another aspect of the momentum equation, which is given to us by this problem. Okay, in this problem we have simply a duct, okay, as he calls it, which we use for testing models, a wind tunnel. The model in this case, it looks like a bullet. It's a bullet shaped, and we want to measure the drag, okay, using the wind tunnel. This at the inlet we're given the velocity to be uniform. At the exit the velocity is not uniform, so we have to be careful. Now when we apply the momentum equation, we're given the pressure at P1 being 1.5, we're given the pressure at P2 being 1 kilopascal gauge. The density of the air is given this 1 kilogram per cubic meter, and we are asked now to determine the drag force on this device. Okay, we will just follow the same procedure as before. We draw the control volume around our subject, which is the model or the device, which looks like a bullet. As you see, observe that because of the flow of the air around this bullet, it will try to drag it with the flow. So يعني تسحب مع الفlow. Because of the support will resist this drag. Okay, so when he drew the free body diagram on the device, we have the drag force of the fluid being the Hawa in our case, and then we have the resistance by the beam. So this is the force that we want to find, which is equal to the support, or the forces provided by the support in both sides. Okay, we have a pressure force because the fluid has a pressure at the inlet P1A1. We observe that the diameter is the same. P2, observe how it's normal and acting on the control volume. Okay, but again in this case we have to observe that the velocity is non-uniform at the exit. So when we apply the momentum equation, we need to write it carefully. In this case, we have the summation of forces plus equal as if the summation of forces equal to time rate of change of momentum inside Z. Now we cannot say the summation because that applies for uniform condition. We have to put the integral like this: control surfaces at out V rho V dot dA, because non-uniform, minus at the inlet we still use the uniform condition because it's uniform. Okay, the forces اللي هي we have P1A1 acting on it minus P2A2 plus the drag force that we are to find steady. Now this term we have to find minus, this is easy, we have basically we're given the velocity being 30 meter per second, so we say the m dot هي عبارة عن rho v area طبعا at the inlet multiplied by v اللي هي عبارة عن v1. So if we want to compute v m dot اللي هي density 1 kilogram per cubic meter, the velocity اللي هي عبارة عن 30 meter per second, and the area اللي هي is given to us being 1 meter in diameter. Okay, alright. Now how can we find the velocity direction or the velocity profile at the exit, because we need it in order to perform this integration. Again, in this case we have the center, and we have at this cross section we have the velocity profile is given to us as in this hypothetical profile being 0 at the center when r equal to 0. This is the coordinate for the r direction, and we have it v max when we reach the radius for this wind tunnel, which is given to us as r naught. Okay, we recognize that it's steady. We can call it incompressible because of the density variation is not that significant. So we have the discharge at the inlet equal the discharge at the outlet. Again, because we can treat it as a steady, which is indeed steady, and the density variation is insignificant as implied by the problem. The discharge at the inlet اللي هو عبارة عن V1A1 because it's uniform. The discharge at the outlet, it's non-uniform. It will be we have to integrate it around the cross-section area اللي هو was given us to as rho v dA. Okay. Now, if we look at the pipe at a cross-section, we will see the pipe in this configuration. At a certain location, we'll see this small dA like a ring. Now the thickness of this one is dr. Okay, so the area associated with this ring dA is basically the perimeter, which is 2 pi r multiplied by dr, okay, instead of dA. That's one thing. Now we go back to the velocity. Velocity here is given as linear, as a hypothetical case. If it's linear in r, it will be given this linear equation. okay, where A and B are constant for this linear equation. Now we say we substitute for r equals 0, velocity equals 0. So when r equals 0, this is 0, velocity equals 0 implies that b is 0. Okay, when r equal r naught, the velocity equal vm, so we have vm equal a r naught implies that a is equal to vm over r naught. This gives us the solution, at least as a first step, for the velocity profile given as vm, which yet to be determined over naught multiplied by r. This velocity profile now we can substitute back into the velocity to find again, I'm making several mistakes, but because this is constant we can drop it from this equation to find Vm. Okay, how do we find Vm? Simple. So again, from the last equation we have V1 A1 equal to the integration. Now we substitute for the velocity profile, which is Vm over r naught r, and instead of the Va we substitute the for r values from 0 to r naught. Okay, observe that Vm and r naught are constant, so is the 2 pi obviously, so this becomes 2 pi Vm over r naught. The integration for r squared, which is r cubed, as r varies from 0 to r naught. Okay, so it will become 2 pi Vm over r naught cubed. Okay, V1, which is given to us, V1 is given to us as 30 meter. area is عبارة عن باي على 4 في الديامتر اللي هو 1 meter square. So pi مع pi goes away and we end up with Vm equal to V1 over 8 على r square. Okay, of course multiply by 1 square. Okay, where r naught is, and it will be 0.5, which is half of the diameter. Okay, 0.5 squared, so that means it's 1 over 4, 1 over 4, so that means V1 اللي هي over 2. It looks like I have made a mistake when I have integrated r squared. I should have divided by 3 like this, and also again divide by 3, and we will solve it for Vm. This becomes 3/2 V1, 3/2 V1. So now we have the velocity profile. We have the velocity profile at the exit, which is given as V equal to Vm, which is 3.5 V1 over r naught times r. طيب نكمل. احنا we want to find the drag force as we said before. We need to find the drag force. The computation of the momentum of flux at the inlet is easy. It's simply m dot v v1, which m dot we compute as we said here. Now the computation of the flux, momentum flux at the exit, recognize that the velocity and the area, the angle between them is 0, therefore this will be VDA. So this becomes v squared r dA, and then we substitute for dA its value in terms of the dr. So the value of this one has become, to evaluate it, let's just do it quickly. So to evaluate the momentum of flux at the exit, we have rho v squared dA. Instead of dA, we'll substitute 2 pi r dr, and again we are varying r from 0 to r naught, which is the radius of this wind tunnel. Okay, and then we have density is constant, we can take it out. 2 pi also is constant, obviously, that's a number. And instead of the v, we will substitute v, 1 multiplied by, which is the value we have obtained previously, 3.5 times r squared, so everything is squared, multiplied by r dr, where r varies from to this one. Okay, again we realize that this is constant, so it will become equal to 2 pi rho multiplied by 3/9/4 because it's squared, multiplied by v1 squared, r cubed integration, so it will become r to the 4th على 4 as r varies from this value. So again, for this integration, I believe I have substituted for the velocity wrong. Let's see if we can go back to it again. For the velocity again, I forgot to put r naught in the denominator, so I should have included r naught here, squared, so it will be r naught squared, so the integration will become 2 pi rho 9 v1 squared over 4 r naught squared r naught to the 4th. So this is the momentum of flux at the exit. Obviously we can cancel, it becomes as seen here, and then we substitute these into the momentum equation to find the drag. Okay. Here he puts it in a simple form, which equal to this. We can see this by recognizing that the area is pi r squared, the density في velocity is equal mass. So we recognize that rho v1 في الاريا اللي عبارة عن pi r naught, this is m dot, so we can, this term, say it's equal to 2 multiplied by 9, we take 1v divided by 4 times m dot, which is the same relation he obtained. Again, it looks like I have got to include this 4, which comes from the integration. Okay, so truly this sigma becomes 9/8 m dot v1. Okay, as he done so in here. Alright, and then the rest is substituting into the momentum equation, which is this equation, So we substitute what we have found from this integration and here to find d1, where everything else is given.